right, so we're going to start talking about combustion. So combustion is a chemical reaction which a fuel is rapidly oxidized and a large amount of energy is released. So you've got fuel plus some oxidizer gives you the products of combustion. The fuel that we're going to talk about, or the type of fuel that we're going to talk about most commonly in this class, are hydrocarbon fuels, and that's just some mixture of hydrogen and carbon. So you've got the X and the Y here, those subscripts, those would just be replaced by numbers. So maybe you've got CH4, that would be methane, so you wouldn't have anything after the C, you'd have 4 after the H. The oxidizer, typically you use the oxygen in the thing that you have a whole bunch of, which is air. But you can use pure oxygen, for example, in welding, that's what they use. But in most combustion reactions that you'll come in contact with, you're using oxygen within the air. And dry air is made up of approximately 79% nitrogen and 21% oxygen. There are other trace gases in there as well, but the majority of it is nitrogen and oxygen. So 4.76 kilomoles of dry air is equal to 1 kilomole of oxygen plus 3.76 kilomoles of nitrogen. And that's just something you're going to have to memorize for this class. So the 79 and 21%, those are mole fractions. So for the mole fraction for oxygen, you got 1 kilomole of oxygen per 4.76 kilomoles of your mixture, your dry air mixture of those two gases. A typical simplified reaction for a hydrocarbon fuel undergoing complete combustion with a theoretical amount of dry air. So there's a lot of stuff in there. We're going to take it one part at a time, but just look at that equation. So the first term, there's your hydrocarbon fuel. The next term, that A sub TH, that's the theoretical amount of air. We'll talk about that in just a second. And then in the parentheses, you got O2 plus 3.76 nitrogen. That's your 4.76 kilomoles of dry air. So you've got 1 kilomole of oxygen, 3.76 kilomoles of nitrogen, 4.76 kilomoles of dry air. Then on the right-hand side, you've got your products of combustion. And the X, Y, Z are coefficients that you're going to have to solve for, because the mass of all the elements of each element has to balance on each side. If you started out with 4 hydrogen on the left-hand side in your reactants, on the right-hand side in your products, you have to still have 4 hydrogen. So you can see you got CH4, so you got 4 hydrogen. And then on the right-hand side, you've got 2 water molecules, but on each one of those water molecules, you've got 2 hydrogen, so 2 times 2 is 4. That A sub TH, that's the theoretical air, the stoichiometric air, it's the minimum amount of air that's required to have complete combustion and convert all of the carbon in your hydrocarbon fuel to CO2, all the hydrogen in that hydrocarbon fuel to water. If you had any sulfur, if you had a sulfur-based fuel, convert all of that sulfur to sulfur dioxide. So it's the minimum amount to have that equation balance. Now you can have incomplete combustion, and that's where smoke comes in. So smoke is just unburnt fuel particles. Reasons for incomplete combustion: incomplete mixing, insufficient time for complete combustion to occur. There's something called dissociation that can be a problem at high temperatures. We're not really concerned too much in this class about the mechanisms for incomplete combustion, but what we are concerned with is sort of hedging the bets in our favor. And so to increase the likelihood that we have complete combustion, we typically use more oxygen than we need, just a little bit more, and we express that as not 50%, as excess air, or we can express it as percent theoretical air, and you'll see what I mean in just a second. So 50% excess air means we have 100% theoretical air, 100% of the minimum amount to make that equation balance, 100% plus 50% theoretical air. So in your chemical equation, when you write your balanced equation, you're going to put a 1.5 in front of that A sub TH, in front of that theoretical air. 200% excess air would be 100% theoretical air plus another 200%, which would be 300%, and you put a 3 in front of that A sub TH. And of course, 0% excess air is just 100% theoretical air, 0 plus 100%, and that would just be a 1 in front of that A sub TH, or just an A sub TH. If you do use excess air, so this, you'll recognize this as the chemical equation for complete combustion of a theoretical amount of air, of dry air, and you've got those three products of combustion, so you've got CO2, H2O, nitrogen. Well, when you put your subscript in front of that A sub TH, so like if you put a 1.5 or a 3, you're going to have to make sure that you remember if you've got excess oxygen, you need to put an O2 there. And then one last term that we want to talk about is the air-fuel ratio, because you have a mixture of air and fuel, right, in your in your combustion process. So your air-fuel ratio is just how you express that. It's the mass of the air over the mass of the fuel, but you need to put that in terms of moles, because when you have this nice balanced equation, all the coefficients in front of each of those terms represent the number of moles you have. So in the number of moles, that would be the term in front of those, that would be the amount of moles that you have. So like if you have a theoretical amount of air, if you solve that A sub TH is 3, if you look back at that equation, in the parentheses, you've got 4.76 kilomoles of air. So it'd be 4 times 3. That would be the number of moles of dry air that you have. And then, of course, the number of moles of fuel that you have, it's the coefficient in front of that hydrocarbon fuel. We'll work a couple of problems like this so you know what I mean. And then you need to multiply by the molar mass of the air or the fuel to get things in terms of the mass. And the molar mass of dry air and the molar mass of the fuels that we'll talk about, those are in table A1. For dry air, it's 28.97. You may just remember that regardless because you use it. But yep, I guess that's it. We'll work a couple of problems where we balance an equation. We calculate the air-fuel ratio for theoretical air and for excess air. Thank you for watching. Let me know if you have any questions.